The morning of June 4, 1942, 200 miles northwest of Midway Atoll, Lieutenant Richard Best rolled his Douglas SBD Dauntless into a 70-degree dive, the perforated dive brakes screaming as they bit into Pacific air. 15,000 feet below, the Japanese carrier Akagi twisted through violent evasive maneuvers, her deck crew frantically attempting to launch Zeros that would never leave the ground. Best's hands moved across controls that shouldn't have existed, hydraulic actuators governing split flaps that had been deemed too complex, too unreliable, too dangerous for carrier operations just 5 years earlier. If you're enjoying this deep dive into the story, hit the subscribe button and let us know in the comments from where in the world you are watching from today. The hydraulic pressure gauge registered 1,400 pounds per square inch, driving pistons that extended perforated metal panels into the 240-knot slipstream. Without these brakes, Best's aircraft would accelerate past 300 knots, structural limits that would turn pullout into catastrophe. With them, he could hold this impossible angle, track the moving carrier, and deliver his 1,000-pound bomb with accuracy measured in feet rather than hundreds of yards. The system performing this miracle had been the subject of heated arguments in Bureau of Aeronautics conference rooms, dismissed by senior engineers as a solution searching for problems it would create. But Ed Heinemann had built it anyway. The hydraulic fluid coursing through lines beneath Best's feet represented more than engineering innovation. It embodied a fundamental rejection of the conservative design philosophy that had dominated naval aviation since carriers first sailed. Hand-cranked dive brakes like those on earlier aircraft required 30 seconds of exhausting physical labor to extend, leaving pilots vulnerable and unable to maintain precise dive angles. Heinemann's hydraulic system accomplished the same task in 2 seconds with the flip of a switch. The path to that moment over the Akagi had begun 7 years earlier, in a cramped design office at the Northrop Corporation's El Segundo facility. Ed Heinemann, 30 years old, and newly promoted to chief engineer after Jack Northrop's departure, stood over drafting tables covered with technical drawings of the XBT Yaden dive bomber prototype. The aircraft represented the Navy's first serious attempt at a modern carrier-based dive bomber all-metal construction, retractable landing gear, and most critically, a solution to the violent tail buffeting that had made earlier dive bomber designs nearly unflyable. The buffeting problem had nearly killed Heinemann during test flights of the early XBT Yaden. Riding as a backseat observer, he had watched in horror as the horizontal stabilizer oscillated through a 2-foot arc during dives, the entire tail assembly shaking with such violence that structural failure seemed imminent. The turbulent vortices tumbling off solid dive flaps were tearing the aircraft apart. Wind tunnel testing at the National Advisory Committee for Aeronautics suggested a radical solution: perforate the flaps with hundreds of precisely tapered holes that would disrupt the vortices while maintaining drag characteristics. Heinemann implemented the perforations on the BT Yaden production aircraft, 318 holes, each 3 inches in diameter, slightly ovalized and flanged to control airflow. The perforated flaps eliminated the buffeting, but they introduced a new challenge that would define the next phase of development. The drag forces acting on these massive perforated panels exceeded anything hand-cranked mechanical systems could reliably manage. Extending solid flaps manually was demanding but achievable. Extending perforated flaps that had to maintain precise positioning while experiencing irregular airflow loads proved nearly impossible with mechanical linkages. The obvious solution was hydraulic actuation. The problem was that in 1935, hydraulic systems in aircraft were experimental technology plagued by reliability issues. Fluid leaks, seal failures, pressure irregularities, and temperature sensitivity made hydraulics suitable for landing gear, where failure simply meant hand-cranking the gear down, but questionable for flight control surfaces that pilots depended on in the most critical phase of combat, operations. Bureau of Aeronautics engineers were divided. Younger officers recognized that hydraulics offered capabilities impossible with mechanical systems. Older hands remembered hydraulic failures that had cost pilots their lives. Heinemann's design philosophy was straightforward: find the most powerful engine available, then design the lightest, simplest airframe around it. But simple didn't mean primitive. It meant ruthlessly eliminating unnecessary weight and complexity while embracing innovations that served clear operational requirements. Hydraulic dive brake actuation served such a requirement. Pilots needed to deploy dive brakes quickly, hold them precisely at varying angles depending on dive profile, and retract them instantly during pullout when every second counted. The hydraulic system Heinemann designed for the XBT-DWA, which would evolve into the SBD Dauntless, used engine-driven pumps to generate fluid pressure stored in accumulators. Pilots controlled brake deployment through a simple cockpit switch that opened valves, allowing pressurized hydraulic fluid to flow to actuators mounted in each wing. The actuators consisted of pistons that mechanically extended or retracted the perforated flap panels. Return springs provided fail-safe retraction if hydraulic pressure failed, ensuring pilots could at least pull out of dives even if the system lost pressure. The system worked beautifully in testing, but it came with weight penalties that troubled Navy procurement officers. The hydraulic pumps, fluid reservoirs, actuators, valves, and plumbing added approximately 250 pounds to an airframe that Heinemann was desperately trying to keep light enough for carrier operations. Worse, the hydraulic system meant the wings couldn't fold, a feature considered almost mandatory for carrier aircraft, where deck space was at a premium. Folding wings required hinges at the wing fold point, and hinges created weak points that couldn't handle the structural loads imposed by hydraulic actuators, extending heavy dive brakes into high-speed airflow. Heinemann made a calculated trade: no folding wings, but massively strengthened wing structure capable of surviving 9G pullouts, loading conditions that would destroy aircraft with folding wing mechanisms. The decision was controversial. Carriers could pack fewer Dauntlesses on their decks compared to aircraft with folding wings. But what they lost in quantity, they gained in capability and survivability. Dauntless pilots could push their aircraft harder, dive steeper, pull out more aggressively, and survive combat damage that would have catastrophically failed folding wing structures. By November 1937, the XBT-DWA prototype had evolved significantly from the original BT Yaden. Heinemann's team had relocated the landing gear from external fairings to recessed wheel wells, smoothing the airframe and improving aerodynamic efficiency. They had added fixed leading-edge slots that prevented stall during the slow-speed maneuvering required for carrier landings. Most critically, they had refined the hydraulic dive brake system to be more reliable, lighter, and faster acting than the original XBT Yaden installation. But reliability remained the central concern. Douglas Aircraft Corporation had acquired the Northrop operation in 1937, and Douglas management scrutinized every technical decision. Donald Douglas Sr., the company's founder, demanded that hydraulic systems prove themselves under the most punishing conditions before committing to production. The XBT-DWA underwent exhaustive testing that would have broken lesser designs. Test pilots pushed the dive brakes to their operational limits and beyond. They deployed them at speeds exceeding design parameters. They cycled them thousands of times, searching for fatigue failures or seal degradation. The system performed. Hydraulic fluid leaks occurred, but they were minor and easily corrected through improved seals and fittings. Temperature variations affected fluid viscosity, but within acceptable ranges that didn't compromise system function. Most importantly, the fail-safe features worked. When test pilots deliberately shut off hydraulic power during dives, the spring-loaded actuators retracted the brakes, allowing normal pullouts. The XBT-DWA demonstrated that hydraulic dive brake actuation was not only feasible but superior to any mechanical alternative. In April 1939, the Navy placed orders for 57 SBD Yaden aircraft destined for the Marine Corps, and 87 SBD-DWA variants for carrier squadrons. The production designation reflected the aircraft's new identity, Scout Bomber Douglas. The name Dauntless came later, assigned by the Navy to an aircraft that. If you're enjoying this deep dive into the story, hit the subscribe button and let us know in the comments from where in the world you are watching from today. It would earn the right to that designation through combat performance that exceeded every expectation. Production SBD aircraft incorporated lessons learned from XBT-DWA testing. The hydraulic system received strengthened fittings at connection points subject to vibration. Fluid reservoirs were relocated to minimize temperature fluctuations. Actuator seals were manufactured from improved materials that resisted degradation from hydraulic fluid and temperature cycling. Perhaps most significantly, the SBD tree variant introduced in early 1941 featured comprehensive hydraulic system improvements that addressed every reliability concern identified during operational use of earlier models. Pilots transitioning from older dive bombers to the Dauntless noticed the difference immediately. Instead of exhausting manual cranking that left them breathless and unable to make fine control adjustments during dives, they simply flipped a switch. The perforated dive brakes extended smoothly, the hydraulic system holding them rock steady despite the enormous aerodynamic loads. Dive angles that had been theoretical possibilities became operational realities. Pilots could push past 70 degrees, holding the nose down through the entire dive, making continuous corrections to track maneuvering targets below. The hydraulic system's most critical advantage emerged during the pullout phase. As pilots reached bomb release altitude, typically between 2,000 and 3,000 feet, they had mere seconds to complete a sequence of actions that determined whether they lived or died. Release the bomb. Begin retracting the dive brakes. Pull back on the stick to initiate the pullout. The entire sequence occurred while the aircraft was accelerating through its dive, with Japanese anti-aircraft fire filling the sky and defending fighters diving to intercept. Manual dive brake retraction during this phase was nearly impossible. Pilots pulling 4, 5 or 6 Gs couldn't generate the physical force required to crank mechanical systems under load. But hydraulic retraction was instantaneous. Pilots flipped the switch, hydraulic pressure drove the actuators, and the perforated panels folded smoothly into their recessed positions within 2 seconds. Those 2 seconds meant lower pull-out altitudes, reduced exposure to anti-aircraft fire, and higher survival rates. The difference between hydraulic and mechanical actuation was measured in dead pilots versus living ones. By mid-1942, the Pacific War had entered its critical phase. Japan's stunning victories at Pearl Harbor, the Philippines, Wake Island, and across Southeast Asia had convinced imperial planners that American will to fight was broken. Admiral Isoroku Yamamoto planned an operation to draw out and destroy America's remaining carrier forces near Midway Atoll, establishing Japanese naval supremacy so complete that the United States would have no choice but to negotiate a favorable peace. But American codebreakers had read Yamamoto's radio traffic. Admiral Chester Nimitz knew the Japanese plan, knew the timing, and knew he had one chance to ambush the Kido Butai, Japan's elite carrier striking force, consisting of the fleet carriers Akagi, Kaga, Soryu, and Hiryu. Enterprise, Hornet, and the hastily repaired Yorktown sortied from Pearl Harbor, carrying air groups that represented America's last offensive capability in the Pacific. Among those squadrons were dive bomber units equipped with Douglas SBD Dauntless aircraft, whose hydraulic dive brake systems had been designed by a self-taught engineer who'd rejected conventional wisdom about what carrier aircraft required. The morning of June 4th began badly for American forces. Torpedo Squadron 8 from Hornet attacked without fighter escort, and Japanese Zeros slaughtered 15 TBD Devastators in minutes. None of their torpedoes hit. Torpedo Squadron 6 from Enterprise and Torpedo Squadron 3 from Yorktown met similar fates. Of 41 torpedo bombers that attacked the Kido Butai that morning, only 6 survived. The Japanese carriers emerged unscathed, their combat air patrol having destroyed the American torpedo threat with contemptuous ease. But the torpedo bomber attacks had drawn Japanese fighters down to sea level at the exact moment when Enterprise's and Yorktown's dive bomber squadrons arrived at 15,000 feet. The sky above the Kido Butai was empty. Below, 4 carriers steamed in formation, their decks crowded with aircraft being rearmed and refueled for strikes against the American carriers that Japanese scouts had finally located. Lieutenant Commander Wade McCluskey, leading Enterprise's Air Group 6, rolled his Dauntless into a dive that 32 aircraft would follow in rapid succession. The hydraulic dive brake system that Heinemann had designed performed exactly as intended during the most important 6 minutes in Pacific naval warfare. Pilots flipped their switches, hydraulic actuators extended perforated panels into the slipstream, and the Dauntlesses held rock-steady 70-degree dives, while pilots tracked their targets through telescopic sights. The hydraulically actuated brakes didn't just control speed, they provided the stability that made precision bombing possible from near-vertical dives. Without that stability, pilots would have been making constant control inputs to compensate for speed variations and turbulence, destroying their ability to maintain sight picture on targets 5 miles below. Lieutenant Richard Best led a 3-plane section that split from McCluskey's main formation to attack Akagi. Best's dive began at 14,500 feet. His dive brakes extended instantly when he flipped the cockpit switch, the hydraulic system responding with mechanical precision that belied the complexity of what was occurring. Pressurized fluid flowed from accumulators through valves to actuators, driving pistons that extended 318-hole perforated panels against air loads, approaching 5,000 pounds per panel. The panels held steady, perforations disrupting vortex formation, while generating massive drag that limited Best's speed to 240 knots. At that speed, Best could track Akagi's violent evasive maneuvers, making fine corrections with stick and rudder inputs that would have been impossible at 300 knots. His bomb sight pipper remained locked on the carrier's rising sun emblem painted on the flight deck. At 2,500 feet, Best pulled his bomb release lever. The 1,000-pound bomb swung clear on its trapeze mechanism, falling toward Akagi, while Best simultaneously flipped the dive. Brake switch to retract. Hydraulic fluid reversed course through the system. Actuators retracted the panels. Best pulled back hard on the stick, the Dauntless responding by curving up from its dive in a pullout that subjected airframe and pilot to forces approaching 8 Gs. A 200-pound pilot weighed 1,600 pounds. Arms felt like lead weights. Blood drained from the brain toward the lower body. Best grunted and strained, forcing blood back up, maintaining consciousness while the Dauntless clawed back toward altitude. The bomb hit Akagi just aft of the midships elevator. The armor-piercing warhead penetrated the flight deck and detonated among aircraft being rearmed with bombs and torpedoes. Secondary explosions ripped through the hangar deck. Within minutes, Akagi was a flaming wreck, her capacity to conduct flight operations destroyed by a single bomb delivered with accuracy that only hydraulically stabilized dive bombing made possible. The technical achievement of that single bomb hit represented the culmination of engineering decisions that had been debated, challenged, and nearly rejected multiple times during the Dauntless development process. In 1938, when Heinemann presented his hydraulic dive brake design to Bureau of Aeronautics review boards, senior officers had questioned whether the added complexity justified the theoretical performance improvements. One captain, a veteran of biplane dive bomber operations, had argued that well-trained pilots could achieve adequate results with mechanical systems that had proven themselves over decades of naval aviation. Heinemann's response had been characteristically direct. Adequate wasn't good enough. Adequate meant higher casualties, lower hit rates, and operational limitations that would cost the Navy battles. The hydraulic system wasn't theoretical improvement, it was fundamental capability that mechanical systems couldn't provide. He demonstrated this with wind tunnel data, showing the aerodynamic loads on perforated dive brakes during 70-degree dives. The forces exceeded what any pilot could reliably control through mechanical linkages, while simultaneously managing throttle, flight controls, and bomb release during the most demanding 30 seconds of combat flying. The data convinced skeptics, but implementation challenges nearly derailed the program. Early hydraulic actuators suffered seal failures during temperature testing. Fluid leaked at connection points when systems cycled repeatedly under load. Procurement officers calculated that resolving these issues would delay Dauntless production by 6 months, potentially leaving the Navy without modern dive bombers at a time when war with Japan appeared increasingly likely. The pressure to abandon hydraulics and revert to mechanical systems was intense. Heinemann refused. The seal failures resulted from inadequate materials, not flawed design. He worked directly with seal manufacturers to develop improved compounds that could withstand temperature extremes and hydraulic fluid exposure. The connection point leaks resulted from inadequate torque specifications and insufficient thread engagement. Engineering drawings were revised to specify proper fitting installation procedures. Within 3 months, the problems were resolved, and testing resumed with systems that proved reliable under conditions far exceeding operational requirements. This determination to solve problems rather than accept compromises defined Heinemann's approach throughout his career. Lesser engineers would have made the hydraulic system optional equipment or relegated it to later aircraft variants. Heinemann recognized that the dive brake system was fundamental to Dauntless capability, that no amount of pilot skill could compensate for inadequate tools, and that engineering challenges existed to be overcome rather than avoided. His willingness to stake his professional reputation on controversial technical decisions separated competent design from transformative innovation. The vindication came not just at Midway, but in every combat engagement where Dauntless squadrons operated. At the Battle of the Coral Sea in May 1942, Dauntless dive bombers from Lexington and Yorktown had damaged the carrier Shokaku badly enough to remove her from the Midway operation. Those attacks succeeded because pilots could hold 70-degree dives while the carrier maneuvered violently, tracking their target through the entire dive, and placing bombs with precision impossible for aircraft with less capable dive brake systems. Japanese Naval dive bombers attacking American carriers during the same battle achieved lower hit rates despite comparable pilot skill, hampered by mechanical dive brakes that limited their dive angles and stability. The performance gap widened as the war progressed, and pilot experience levels diverged. By late 1942, Japan was losing its elite carrier pilots faster than training programs could replace them. American pilots, meanwhile, were learning to exploit every capability their aircraft offered. Experienced Dauntless pilots discovered they could modulate hydraulic dive brake deployment to control their rate of descent precisely, holding specific airspeeds that optimized bombing accuracy for different target types. This level of control was impossible with mechanical systems that offered only binary extended or retracted positions. Squadron commanders incorporated hydraulic system management into dive bombing doctrine. Training emphasized smooth brake deployment to avoid sudden airspeed changes that disrupted aim. Pilots practiced partial brake extension during approaches to conserve altitude while maintaining formation positions. The hydraulic system transformed from a mechanism for extending metal panels into an integral component of combat technique that skilled pilots exploited to maximum advantage. The system's flexibility enabled tactical innovations that mechanical alternatives couldn't support. McCluskey's main formation had targeted Kaga, the second carrier in the formation. 25 Dauntlesses rolled into their dives in rapid succession, each pilot executing the same hydraulically enabled attack profile that Best had demonstrated against Akagi. The dive brake switches flipped almost simultaneously, and hydraulic systems across 24 aircraft responded with identical precision. Perforated panels extended, biting into the air, stabilizing the formation as it plunged toward Kaga's deck. The concentration of bombs falling from stabilized platforms overwhelmed Kaga's ability to evade. 4 direct hits and several near misses transformed the carrier into an inferno within minutes. Like Akagi, Kaga's hangar deck was packed with armed and fueled aircraft. The bombs from McCluskey's Dauntlesses triggered cascading explosions that gutted the carrier from within. By 0930 hours, Kaga was dead in the water, her crew abandoning ship as fires raged out of control. Simultaneously, 17 Dauntlesses from Yorktown's Bombing Squadron 3, led by Lieutenant Commander Maxwell Leslie, had located Soryu, the third carrier in the Japanese formation. Leslie's attack demonstrated another critical advantage of hydraulic dive brake actuation: the system's reliability under combat damage. Several of Leslie's aircraft had been hit by anti-aircraft fire during their approach, suffering damage to control surfaces and airframe structures. But their hydraulic systems remained functional, allowing pilots to execute proper dive bombing attacks despite aircraft that were barely airworthy. Leslie's own bomb had been accidentally released during the approach due to an electrical fault, but his wingmen compensated. 3 bombs struck Soryu in rapid succession, hitting near the forward elevator, amidships, and aft. The pattern of hits reflected the precision that hydraulically stabilized dive bombing enabled. Pilots weren't simply aiming at carriers, they were placing bombs on specific sections of flight decks with accuracy measured in feet. Soryu's fate matched that of her sisters. Within 20 minutes of the first bomb impact, she was burning uncontrollably, her crew fighting fires they couldn't extinguish. The destruction of 3 fleet carriers in 6 minutes represented more than tactical success. It validated a chain of engineering decisions that had begun with Heinemann's determination to implement hydraulic actuation for dive brakes, despite widespread skepticism about the technology's reliability. The hydraulic systems performed flawlessly under conditions that would have broken mechanical alternatives. Pilots who had never experienced combat stress before successfully operated complex hydraulic controls while pulling multiple Gs, tracking moving targets, and evading anti-aircraft fire. Later that afternoon, dive bombers from Enterprise and Yorktown located and attacked Hiryu, the 4th Japanese carrier that had escaped the morning strikes. Once again, hydraulically actuated dive brakes provided the stability and control that made precision attacks possible. Hiryu suffered multiple bomb hits that left her as devastated as her 3 sister ships. By evening of June 4th, all 4 carriers of the Kido Butai were sinking or had already sunk. Japan's elite carrier striking force had been annihilated by aircraft whose critical systems had been considered too experimental for operational use just 7 years earlier. The technical significance of what occurred at Midway extended far beyond the immediate tactical results. The battle proved that hydraulic actuation wasn't just feasible for critical flight systems. It was superior to mechanical alternatives in every measurable way. The Dauntless dive brake system had performed under the most demanding conditions imaginable: high G maneuvering, extreme altitude changes, temperature variations from 15,000 feet to sea level in seconds, and the vibrations and stresses of carrier takeoffs and arrested landings. Not a single hydraulic system failure was recorded during the battle. This validation transformed naval aviation procurement. After Midway, hydraulic actuation became standard for dive brakes, flaps, landing gear, and eventually flight control surfaces on carrier aircraft. The weight penalty that had troubled procurement officers in 1939 became acceptable. Once combat results demonstrated the operational advantages, aircraft designers gained confidence to implement increasingly sophisticated hydraulic systems that enabled capabilities impossible with mechanical controls. The engineering principles that Heinemann had applied to the Dauntless dive brake system influenced his subsequent designs throughout the war and beyond. The AD Skyraider, which became the Navy's premier attack aircraft in the Korean War, featured comprehensive hydraulic systems controlling nearly every movable surface. The H-Derry Skyhawk, designed in the 1950s, used hydraulic actuation so extensively that mechanical backup systems were minimal. Each generation of aircraft built upon lessons learned from the Dauntless, incorporating more sophisticated hydraulic technology that traced its lineage directly to Heinemann's 1930s engineering decisions. But the immediate impact was measured in pilots who survived combat because their dive brakes worked when needed most. Lieutenant Norman Dusty Kleiss, flying from Enterprise, executed attacks at Midway that required pullouts at 9 Gs forces that approached the structural limits of the airframe. In his post-war memoir, Kleiss described the dive brake retraction during pullout as the difference between living and dying. Manual systems couldn't have retracted under those G-loads. The pilot would have been trapped in a slower, shallower pullout that left him exposed to anti-aircraft fire for fatal seconds, longer. The hydraulic system's performance, under extreme G-loading, revealed sophisticated engineering that wasn't immediately apparent. Hydraulic fluid under pressure behaves differently than atmospheric pressure fluid. At 9 Gs, fluid in the reservoir experienced forces 9 times normal, potentially causing flow irregularities or cavitation in the pumps. Heinemann's design incorporated baffles in the reservoir that prevented fluid surge and pump inlets positioned to ensure constant fluid supply even under extreme maneuvering loads. These details never appeared in specifications or procurement documents, but they represented the kind of deep engineering thinking that separated adequate designs from exceptional ones. The perforations in the dive brakes themselves embodied similar attention to aerodynamic detail. The 318 holes weren't simply drilled through metal panels. Each hole was precisely tapered and flanged to control how air flowed through the perforation. The taper prevented turbulent vortices from forming at the hole edges. The flanges directed airflow to minimize buffeting on the horizontal stabilizer. Wind tunnel testing at NACA had determined the optimal hole size, spacing, and geometry through hundreds of hours of testing that predated the first BT Eden prototype. The combination of optimized perforation geometry and hydraulic actuation created a system where the hole exceeded the sum of its parts. The perforations controlled aerodynamic forces on the panels, reducing the loads the hydraulic actuators had to overcome. The hydraulic actuation provided precise control over panel position, allowing pilots to partially deploy dive brakes for variable drag, depending on dive angle and speed. Pilots learned to use partial brake deployment during formation maneuvering, a technique impossible with mechanical systems that offered only fully extended or fully retracted positions. Japanese naval aviation examined captured Dauntless components after the war, trying to understand what had made the aircraft so effective. Their analysis revealed surprises. Japanese engineers had assumed American dive bombers used similar mechanical dive brake systems to their own Aichi de Tria Val dive bombers. The discovery that Dauntless brakes were hydraulically actuated, with sophisticated fail-safe features and precise control characteristics, explained capabilities Japanese pilots had observed in combat. American dive bombers could hold steeper dives longer, execute more aggressive pullouts, and place bombs more accurately than Japanese aircraft with comparable performance parameters. This revelation was particularly frustrating because Japan had experimented with hydraulic systems on experimental aircraft, but had never committed to production implementation. Japanese engineers recognized the advantages, but couldn't overcome manufacturing challenges. Hydraulic actuators required precision machining and quality seals that Japanese industrial capacity struggled to produce in quantity. The gap between recognizing good engineering and implementing it at scale revealed fundamental differences in industrial capability that extended far beyond individual aircraft systems. By 1943, the Dauntless was being supplemented by the Douglas SBD Helldiver, which featured even more extensive hydraulic systems. But many pilots preferred the older Dauntless, not despite its simpler systems but because of them. Heinemann's design philosophy of ruthless simplification meant the Dauntless had fewer components to fail. The hydraulic dive brake system was complex enough to provide required capability, but simple enough to be maintained by carrier deck crews under combat conditions. This maintainability proved critical during extended carrier operations in the Pacific. Squadrons operating from remote anchorages lacked sophisticated maintenance facilities. Mechanics kept Dauntless hydraulic systems functioning with basic tools, replacement seals, and hydraulic fluid. The system's fundamental simplicity, engine-driven pump, accumulator, valves, actuators, meant troubleshooting was straightforward. When leaks developed, mechanics could trace hydraulic lines, identify failed seals, and replace them without removing the entire wing. The contrast with the Helldiver was stark. That aircraft's more sophisticated hydraulic systems offered theoretical advantages but practical maintenance nightmares. Carrier crews nicknamed it the Beast, partly because its hydraulic systems were notoriously temperamental. Pilots who had flown both aircraft universally praised the Dauntless for reliability. In combat, reliability trumped sophistication every time. Marine squadrons continued flying Dauntlesses until the war's end. Long after Navy carrier squadrons had transitioned to Helldivers, the Marines appreciated the aircraft's ruggedness and the simplicity of its systems when operating from primitive island airstrips. Hydraulic systems designed for carrier operations proved equally capable operating from coral runways, where dust, heat, and limited maintenance resources challenged every aircraft system. The Dauntless accumulated an extraordinary combat record beyond Midway. At the Battle of the Philippine Sea in June 1944, Dauntless dive bombers from carriers participated in what pilots called the Great Marianas Turkey Shoot, helping to shoot down hundreds of Japanese aircraft. The hydraulic dive brakes that had stabilized bombing runs also improved maneuverability during air combat, allowing pilots to rapidly reduce speed and tighten turns when engaged by fighters. Several Dauntless crews scored air-to-air victories against Japanese fighters, achievements that would have been impossible in less capable aircraft. Statistical analysis of Dauntless combat operations revealed performance characteristics that validated every engineering decision Heinemann had made. The aircraft sank more enemy shipping than any other Allied bomber in the Pacific. It achieved air-to-air kill ratios that exceeded expectations for a nominal bomber. Most remarkably, it demonstrated survivability rates significantly higher than comparable dive bombers. Pilots brought shot-up Dauntlesses back to carriers with damage that would have destroyed lesser aircraft. The structural strength Heinemann had designed into non-folding wings allowed the airframe to absorb punishment and keep flying. The hydraulic dive brake system contributed directly to survivability. Damage to one wing's hydraulic actuator didn't prevent the other wing's system from functioning. Pilots could deploy dive brakes asymmetrically if necessary, compensating with rudder and aileron inputs. This redundancy wasn't explicitly designed into the system. It emerged naturally from having independent actuators on each wing rather than a single mechanical linkage. Combat revealed capabilities the designers hadn't fully anticipated, but which emerged from fundamentally sound engineering principles. Ed Heinemann never claimed the Dauntless was perfect. In post-war interviews, he identified design decisions he would have changed with hindsight. But the hydraulic dive brake system wasn't among them. That system performed exactly as designed, under conditions more demanding than testing had simulated, with reliability that exceeded even optimistic predictions. It represented engineering at its finest, identifying a clear requirement, implementing proven technology to meet that requirement, and ruthlessly simplifying the implementation to ensure reliability. The broader lesson that Midway taught about hydraulic systems influenced aerospace engineering for decades. Modern aircraft depend on hydraulic systems so extensively that failures are catastrophic. Flight control surfaces, landing gear, brakes, weapons systems, all hydraulically actuated, all descended from engineering principles validated when Dauntless pilots flipped switches over the WWII and their dive brakes extended precisely as designed. The hydraulics operating Boeing 747 control surfaces trace their conceptual lineage to Heinemann's determination that mechanical systems weren't adequate for carrier dive bombers. By war's end, 5,936 Dauntlesses had been produced. Most were scrapped in the post-war drawdown, melted for their aluminum at a time when the nation was eager to forget wartime austerity. A handful survived in museums, preserved examples of the aircraft that won Midway. Restoration crews who maintained these museum aircraft discovered that the hydraulic systems, properly preserved, remained functional 7 decades after manufacture. Seals needed replacement, fluid needed changing, but the fundamental components, pumps, actuators, valves, were machined with such precision that they still met specifications. Depression-era American industrial capability had produced components that lasted generations. When aviation historians analyze the Battle of Midway, they focus on intelligence advantages, tactical decisions, and pilot courage. These factors were decisive, but beneath them lay engineering decisions made in drafting rooms years before the battle. The hydraulic dive brake system that Heinemann implemented on the Dauntless gave American pilots capabilities their Japanese counterparts couldn't match. It allowed steeper dives from higher altitudes, provided stability during the dive that made precision bombing possible, and enabled aggressive pullouts that maximized pilot survival. The system had been controversial when proposed. It added weight, consumed power, required maintenance, and represented unproven technology for critical flight systems. Conservative engineers had argued for mechanical alternatives with longer track records. But Heinemann had recognized that operational requirements demanded hydraulic actuation, regardless of procurement office concerns. about maturity and reliability. He built the system, tested it exhaustively, and delivered an aircraft whose critical systems performed flawlessly during the most important carrier battle in naval history. The morning of June 4, 1942, validated decisions made in El Segundo, California, design offices during 1937 and 1938, when Richard Best's hydraulic actuators extended his dive brakes at 14,000 feet over the WWII. They performed exactly as Heinemann's team had designed them to perform. When those same actuators retracted the brakes during Best's 8G pullout, allowing him to escape anti-aircraft fire and climb back to altitude, they demonstrated reliability that skeptics had claimed was impossible. The engineering was sound, the testing had been thorough, the implementation was robust. Thank you for watching. For more detailed historical breakdowns, check out the other videos on your screen now, and don't forget to subscribe.